So there's only really one required special resource for the course. You've all seen it in lab yesterday. It's digital, right? And digital is that simulator that we use to simulate the digital circuits we're going to be playing with. Like I was saying yesterday in lab, it's an idealized, wait, did I start recording? Yes. It's an idealized simulator in that it doesn't include some of the physical limitations that we would have in real life, but that's not to say like, that's by design. We don't want those limitations that we would have in real life. They're a pain that we have to deal with as a consequence of how we build things like transistors. It's a property of the wires that cause these weird issues in real life, but in digital we don't have to deal with those things, which is nice. There will be some things that digital does do as in terms of like a limitation in terms of like delays for how long transistors take to like flip or something, but that's kind of important for this type of stuff. In general though, it's a very idealized simulator in a very good way. We like that. It's not like it was implemented lazily. It was implemented going like, yeah, we don't want these limitations. We want to have like the theoretical build of all that stuff. And here is a screenshot of part of a working Turing-complete computer. It's just a screenshot. Our goal this semester is we are going to be working towards building an 8-bit computer. And we aren't going to build our computer like this. Like we were talking yesterday, this is actually using IC chips, although they're represented a little bit differently. But these boxes are like integrated circuit chips, which have things like registers in them or AND gates and stuff that we are going to be learning about. For us, though, we're going to be explicitly putting in like the registers, and you'll see. We're going to have a better representation of the computer as we go. I was doing this kind of like a verbose way, deliberately as if it was being physically built, but we're going to be taking advantage of all the tools and abstraction we have within digital in a nice way. This course does have several recommended supplementary resources. None of them are required, but will give you a lot of additional practice. And like if you were to go through these resources, like you're going to be an expert in this content pretty quickly. At the end of each topic, although this isn't true yet, a lot of them are, only the early topics have this. Could I get you to move your bag? Only because I know I'm going to trip over it. I can't stand still when I lecture, so I need to pace. What was I saying? Yeah, at the end of each topic, I might have like some recommended readings or like things to do, maybe watch a YouTube video or something that gives a little bit more detail on something to come or something we just talked about. That's only there as of right now. Like that's the plan for the course in the end. As of right now, only the first few topics have that. Right now, if you go later in the course and you're like TBD, 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 yeah, I know. It's just I have it like that for now. Okay, this course content is all available on GitHub, like I already showed you. If you go to that link right here, all of this is all of the course content I have for the course, if it will load. And it's basically a giant folder stored on GitHub that contains everything you need for generating all the course content. This includes things like some of the digital files that we're playing around with, and all of like the source for generating there's some scripts in there, but all the stuff for generating the actual website. It's all here. It's entirely possible if you see a typo, you can go edit the typo and submit something on GitHub to fix the typo. If you think something could be explained better, I would encourage you to explain it and put it on GitHub, and then we can incorporate it into the course. Like I very much encourage this. There is like a little README down here. Just have a look at the README. But yeah. The textbook, pardon me, the textbook is Introduction to Computing Systems from Bits and Gates to C and C++ and Beyond. This textbook, the contents of this course won't cover the entirety of the textbook. There's going to be a bunch of content in this course that's like outside what's in the textbook, but the textbook starts with like where we're starting in the course, but ends with like programming in C and C++. We're not going to get to there. Intentionally, we're not going to get to there. So the textbook is like it's got a lot more content than we would need, but overall it's a pretty good textbook. There's also there's this guy named Ben Eater. He's got a series, he's got a lot of YouTube videos with a shockingly large number of views for content like this. Like we're talking like millions, which is weird because it's like millions of people are watching videos on how to build computers like this, and yeah, they are. He's got a playlist on building a full 8-bit computer on breadboards, which is like the one I have in my office if you ever see it. Here's a picture of it. But you can watch his videos. I mean, it would take time to go through the videos, but he is phenomenal. He's really good at explaining things, and it's just kind of cool to see him talk about these things, which is really neat. And here is a picture of like the breadboard computer I have in my office. Technically, this computer is not complete. It's not Turing complete yet. I have like one last thing I have to do, and it's been sitting there on my to-do list for like 2 years, and I haven't done it. Maybe 3 years now, 4. Man, that was like 2020. Yeah, I should probably finish it. But anyways, it's a breadboard computer, and it can do a lot of stuff. It's just not Turing complete yet, which is a whole thing. Raise your hand if you know what Turing complete means. Yeah, that's fine. You don't have to at this stage. It's fine. It's not. It has a limitation in what it can compute that like your computers don't have. Now, when I say limitation, obviously this computer is limited in that like it's built on breadboards. Those are called breadboards, by the way. Those little these little like boards with like holes in them. It's built on that, and it's only 8-bit. It has an 8-bit bus. These are all things we're going to be learning about this course. So obviously it's constrained in that way, but when it is Turing complete, it technically can compute within its constraints of like bit size. Like the stuff that it could compute is like the same that like your computers can compute, although it's constrained to only 8 bits. What that means might be hard to understand at this stage, and that's fine, and that's something we're going to work towards. All right, and here's a weird one. Another piece of supplementary information or supplementary resource I would recommend for this game is a game you can buy on Steam called Turing Complete. And you actually start with things like what we're talking about. You don't start with transistors. In this game, you start immediately with logic gates, but we're going to be covering logic gates pretty soon in the course. And you work to building a far more complex computer than we're going to build in our course in our simulator. And this is a game. It's a fun game that you can play. It's annoyingly not as cheap as you would want it to be. It's not expensive, but I remember being like, really? I can't remember how much it is. Someone look it up on Steam real quick. Actually, it might be linked right here. Let's see. The internet's being really slow today. Do you see? You're looking it up. See if you can beat me. You probably will, because I don't know what's going on here. Well, we'll see. Like, I'm legitimately recommending you buy this game and you play it. If you do, you'll be a wizard in this course. All right, what do we have? See, $23. Like, I'm annoyed. Like, if this was like $8, you'd be a fool not to buy it. But I get it. You look, it's 23, and you're like, eh. It's pretty good. I had a blast with it, and you'll learn so much. You'll learn way more stuff than like what we will cover. But it's a phenomenal game, and if you do buy it and you work through it, like this course will be a cinch for you, I bet. We will be covering some of the nuance that this game won't get into because some of the nuance is kind of like, it doesn't fit well into a game, but yeah. Yeah, and you do incrementally work towards building a Turing-complete computer. In fact, you actually make different Turing-complete computers. You make one, and then you make a more advanced one with a little bit more bells and whistles on it. Technically, it's not more powerful than the other one. Of course. Like 2 seconds ago, I closed it. What was I saying? Yeah. And you start programming it with like assembly code, and like you end up like making a game in it, and that runs on your simulated computer. It's pretty cool. All right. Any questions at all about anything? This is all still like intro stuff. Thanks. You're too late. All right, this is it. This is the one day people are allowed to be late. Next time, I'm closing the door and you're not getting in. When the class starts, it starts. That's it.
I have to live here.
So, yeah, Turing Complete's good game. Yeah, so any questions about any of this? It's just intro stuff. Okay, so I lied to you yesterday. I said that we were going to be covering the transistors and why it needs to be, those gates need to be connected to like power. I lied. You'll see that in a couple of topics. I jumped the gun. I thought we were hitting it earlier than we are. For next time, couple of things. Get your computer set up for the course, like Get Digital and whatnot. I recommend starting to watch, go watch that YouTube video. I don't know how long it is, but it's not too long. Pretty good YouTube video. If you get that game, play that level. You'll have fun. It's the first one. You'll have fun. And if you play it, you might have a hard time not playing the next one, but maybe don't jump too hard, otherwise the course will get boring. And read chapter 1 of your text. That would be like my recommendation going forward. Okay, any questions? Okay, it's fine if you have no questions, but in general, you got to be asking questions, right? Because it gets so boring just talking at you. If you have a question, ask a question, of course. Oh, there we go. If you have a question, ask a question. And chances are, if I'm explaining something and it's unclear to you, ask the question because it's probably unclear to everybody else in the room too. So be the hero everybody needs and ask me so I can explain it better. And like I was telling you last time, this is brand new content I've made. So if something's unclear, you gotta let me know by asking for more clarity, and then that lets me know how to improve the content. Just smiling and nodding doesn't do anybody any good, okay? It doesn't do you any good, it doesn't do any other student any good, and it doesn't do me any good, and it doesn't do future students any good. Ask, okay? Again, I know that last thing was like intro, there was no real content there, but I'm just in general, okay? Cool? Any questions? All right. All right. First, we're going to talk a little bit about numbers. But I want to make sure, so first of all, raise your hand if you know how to count to 10. Great. You know what's funny? Unless you've had me before, though, where I've kind of gone over this with you, despite knowing how to count to 10, you might not really know what you're doing when you're counting to 10. It's a weird thing, because of course you know how to count. But you probably haven't really thought about what you're doing. In fact, when you learned to count, you probably learned in a way where you just memorized what to do, and you never really learned about the underlying process that was going on with counting. Which sounds ridiculous, but we're going to talk about it. And we're going to see that counting, regardless of what number base you're in, which is what we're talking about, I'm going to explain this, works the same way. Just we have different limitations or less limitations, depending on how you want to look at it. Another thing I want to emphasize is in this topic, we're going to be working towards binary. But, you know, binary, 0, 1, 0, 1, 0, 1. Oh, that means the number whatever, right? But we got to be very careful. Very, 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 very careful. And I'm warning you this because I know you're going to fall for it, despite me warning you. And it's a weird idea. The pattern 0, 1, 0, 1. Who can tell me what it means?
3, 4, no, 5.
No, you're wrong. If that came off too rude, that was not my intention. So tell me why you said it was 5.
4 is, well, 1, 0, 0 is 4 in binary.
Yeah.
Add 1 to the end.
See, you fell for the classic
Zero at the
mistake.
beginning, so I don't know.
The leading zeros don't matter. So let me show you what I mean, right? So if you don't know binary, that's fine. Okay, 0, 1, 0, 1. And you said, well, that's 4. 5, pardon me. I know why you said that, but you're wrong. And the reason is, I never said that was a binary number. I said, tell me what the pattern means.
Binary string. I don't know.
It's a pattern. That's all it is. That is an encoding. Presumably, it's an encoding of information. In the same way, like if I write this, and if it feels like what I'm about to do, like if the explanation that is to follow sounds like I'm trying really hard to be like philosophical, I'm not. This is an important concept, and I'm not like, yo, dude, that's not what this is. What is that?
3 letters.
3 letters, correct. But does it have a meaning?
Depends on context.
You know what? You're raising a very good point. Now, that's the point I'm trying to make here. 0101, what does it mean? I don't know. That is an encoding of information, presumably. In order to decode that information, think of it like a function, right? I've got info. Can you see that reasonably well back there? Yeah. It goes into something, and it gives me an encoding, right? This will be called like an encoder. It takes some information and it changes it somehow and encodes it somehow. This is the word cat. I encoded it. Like, what does it mean? Well, it means a cat, right? Right? A little cat. I don't know. I'm making it worse. Whatever. It's a cat, right? What is that? That's a cat. I've encoded. I don't know what that is. Let's just leave it alone. You know, they have their little triangle noses, right?
They have a tail sticking out the back.
There you go. There, thank you. So maybe it looks like a mouse. Let's pretend it's a cat. They both like, well, what does this mean? Well, it's a picture of a cat. It's a cat. What is this? Well, it's a cat, right? Like they're both like encodings of cats, but I use like a different encoding. One is a word to mean cat. One is a picture to mean cat. But I've encoded information in my head. When I'm thinking of a cat, I mean, look, we could play this game for a while. What am I picturing? I'm picturing a cat, okay? Really, I just have like signals in my brain that mean cat, but like I've got something. And I want to communicate this idea to you. So how do I do it? Well, I can encode that information. I have information in my head. I'm thinking of a cat. And I want everyone in this room to think of a cat. So how can I do that? Well, I have information in my brain, and I want to put that information into your brains. So how do I do it? I encode that information through sound, cat. You hear it, you decode it, you think cat, and now you're thinking of a cat, okay? There was an encoding of information. It changed its like shape. It got to you, and you unchanged the shape back to cat, okay? I encoded it with sound. I encoded it with a picture. I encoded it with letters, okay? You have a question?
Oh no, just to add on. I mean, I guess it also sort of depends on the fact that we also have the common knowledge of a cat.
Yes, you can decode it, right? It's possible that someone that doesn't know English, they'd be like cat, oh, right? And that's a decoding issue, really. That's it. But I've encoded information 3 different ways. But like, maybe this is an acronym. Maybe CAT stands for something, right? Meaning this encoding might have different meanings depending on how I'm to decode it. Okay? What information did I encode, and how do I decode that information? What information is this, and how do I decode it? You said it's the number 4. 5. I keep doing that. Why am I doing that? Right? We're going to learn why it's 5 if it's not clear to you. That's fine. But it's an encoding. 0101, yeah. If it's a number, if that is a representation of a number, it's 5. But it might not mean that. So disassociate these patterns from numbers. Now, Despite that, what I just said, it is very common for me to say, think of the binary pattern 5, right? And you're like, okay, well, that's 0, 1, 0, 1, right? But I might not really mean that, like, okay, that means the number 5. I just say 5 as an easy way to say what the pattern is. We'll see as we go. The point I'm making is that's not necessarily a number. It's just a pattern. And what does that pattern mean? It depends. Okay? That's the point I'm making. And if you're like, okay, yeah, great, big hand, wavy, oh, meaning. What is the meaning of things? Yeah, that's what I'm talking about right now. Because that's going to be a common thing. And the best part is when we're designing our computer, we get to invent the meaning of things, which is pretty cool. Anyways, decimal. You're used to using decimal, base 10 numbers, okay? How many different symbols do we have in base 10? I'll give you a hint, base 10. How many? 10. Why? You're like, well, there's only 9. No, don't forget 0. 0 is important. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 different things, right? What's neat about integers, if you didn't know this, is they have an intrinsic ordering to them. When I say intrinsic, I mean like it's like a property of themselves. There's an ordering. 0 comes before 1, which comes before 2, which comes before 3, and so on, right? There's an order. And you all know this order. You've all known this order since you were this tall, right? There's nothing to, maybe a little tall, who cares? Somewhere around here. Okay, you will all know this ordering. And usually, if we're using these symbols to represent integers, we know what they mean. The symbol 5 means 5. Now, is that a quantity? Maybe. Is it an abstract number? Maybe, whatever. It means 5, right? Okay, usually it means 5. It could mean something else, but it usually means 5 if we're talking about integers. Right? 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 Right. And so like they convey like a magnitude. So far, so good? And this magnitude does obviously correspond to the ordering. Okay? Cool. It's funny, you've all known this for a long time, but you don't really, mathematicians obsessed with like overly and formally defining things, but no one explained it that like counting to you when you were 4, like this, right? You just kind of learned how to count, and that's fine. But it's important to think about these things. So how do we count in base 10? Now, for those of you that have had me before, you've probably seen me do this. Let's start counting in base 10. We have 10 different symbols. Where do we start? Let's start at 0. Okay, what comes after 1? What comes after 0? 1. What comes after 1? Then what? And 3 means 3, right? 4, what's 4? 5, 6, 7, 8, 9. And like 8 means 8, 9s mean 9. But I'm out of symbols. There's no more symbols. I only have 10 symbols. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But I got more integers I want to represent. I want to represent the number 10. I don't have a symbol for the number 10. So what do? Well, we all know that 10 is 1, 0. Right? We all know that. But what happened? Well, first, remember, with integers, there's always leading zeros. Leading zeros they mean nothing, but like, they exist, right? There's like a place there. How many, and think about it too, right? With base 10, it's always like, well, how many 1s do I have? How many 10s do I have? How many 100s do I have? So if I have like 1, 1, 1, I have 1 100 plus 1 10 plus 1 1, right? That's how it works. So when I have the number like 3, how many 10s do I have? 0. So like there's an infinite number of leading zeros. So what do I do? How do I get to 10? Well, whenever you run out of symbols, you restart, right? But we go to the next place and we increment. So what comes after 0? 1. 1, 0, 1, 1. We increment, and so on. Eventually I get to like 19. What do? Well, I wrap back to the 0, and I increment this to 2. And this follows that idea of like, well, like think of going from 9 to 10. I have 0 10s and 9 1s. I now have 1 10 and 0 1s. Well, that's 10. This is the pattern. Eventually I get to 99. What do? I reset. Oh, I reset. Oh, increment. That's how we count. And you know, I know you know this, but you probably don't think about it like this. But the reason like I know you know this is like, you know, addition is just fancy counting, right? Usually when we start to like define, you can start defining basic arithmetic with the axiom of like, we have to start with like, okay, we can count. And if you can count, well, if I say like 4 plus 5, that means like count 5 times from 4, right? Plus means is like an operator for counting multiple times. Multiplication, it means like do addition multiple times and so on, right? And like if I were to say like 6 plus 7, right? And you go, okay, well 6 plus 7, that's 13, right? 3, carry the 1. That's what we just did, right? We just like carried. So this counting, you've been doing it forever. You just don't think about it. But that's how counting works in base 10. And it's base 10 because we have 10 symbols, 0 through 9. 0 is a very important symbol, but yeah. And it's a positional number system, meaning where the number is relative in the context of the whole number has a very important meaning. Any questions about what I just did? It might be weird, like obviously what I showed you, you all know, but you may not have ever thought about it like this. But that's what we're doing, okay? So we're counting in base 10, 0, 1, 2, 3, 4, 9. How do we get to 10? Well, loop back, increment the next number, right? However, there's only 10 unique symbols. This means it's not possible to count past 9 with the symbols alone. So this is where symbol position comes in. Position, I'm just reviewing what we just did, but I don't want to rush through it. I want to make sure we're hitting it. So first, consider that each number has an infinite number of zeros in front of it. Why this is will be discussed later. Well, we just kind of talked about it, right? Like, and the number 4, how many millions are there? Well, there's no millions in the number 4. There's no 100,000. Oh, no 100,000s, no 10,000s, no thousands, no hundreds, no. Right? So like the number 4 doesn't need these numbers, but they exist because really there's nothing there. Just if we don't write them, and this would work for binary too, or any other number system. If we don't write a leading 0, it's presumed to be 0, right? Like if I don't write the digit out front, then it's a 0. So consider the below table where only 7 of the leading zeros are included. Yeah. So here we have like 8 digits, right? Thus, these numbers will each have a total of 8 symbols. Each of these symbols, numerals, in this context is called a digit. And digit comes from the Latin called digitus, meaning fingers or toes, which is funny, of which we usually have 10. Humans are obsessed with base 10. I don't know if it's because we have 10 fingers, but I think it's because we have 10 fingers, right? We really like this, right? So there we go. Cool. Cool, cool, cool. To count past 9, we need to introduce a new rule. Okay, there's no more symbols. What do? You reset the symbol to 0 in the current position. Change to the subsequent symbol in the next position. So like 8, 9, and then what do? Okay, restart to 0, change to the subsequent symbol, right? 18, 19, reset to 0, change the subsequent in the next position, and so on. Cool, cool, cool. That's how we count. I know. Second year university, and you're learning how to count. And it just keeps, this pattern goes forever. Okay? It's as simple as that. So consider the number 101. Although this number contains 2 ones, they have a different meaning because of their position, right? So 101, 101. We have 100. Do you remember being in like grade 2 and having those little cubes? Do you remember that? Where you'd have 1?
I think we use those all the way up to grade like 6.
Maybe, yeah? If you don't remember, I'm going to try to draw. Wait, you know what? It's funny. I didn't think of this until right now. And I just got like projected back to grade 2, and I'm like, whoa. Sheesh. Of 10 yellow. Were yours yellow? Mine were yellow.
It depends. We started with like wooden ones, but then we got like plastic orange ones.
Yeah, these things. Yeah. So, yeah, this is amazing. This is exactly what I was envisioning in my head, right? So you have these little cubes, individual cubes, and then you have groups of 10. So how many groups of 10 do I have? If I have 3 groups of 10 and 4 ones, that's 34, right? Yeah. It's funny, though, because you're going to be like, yeah, obviously, but this only makes sense, like this is only so obvious because it's base 10. You've been using base 10 since you've been this big, and you've been learning it your whole life, right? So you're like, well, 34, 3 tens, and obviously it's 34. But these same patterns are applied to different number bases, and it's going to throw you off. Despite it being exactly the same, you're just used to base 10. And that's great and all, but yeah, you have a question?
I think, well, when I was in grade 5, we had a substitute teacher one day, and I think he attempted to explain to us base 2, and
it didn't work? Yeah, okay, so although the number contains 2 ones, 101, those ones have entirely different meanings based on where they are in that number. Do you agree? All right? This number 1 and this number 1, they have different, like, significance. Okay, names. Where am I going with this? Okay, each of these positions has a name from left to right. From left to right? I think I mean right to left. Yeah, I mean from right to left. There's a typo someone can fix on GitHub real quick if they're feeling bold. First digit is the ones digit times 10 to the 0, right? There you go, cool. The second digit is the tens digit times 10 to the 1. If you have a 1 in that position, like you get a 10. And this is painfully obvious to you, right? Tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, and so on and so on and so on. We know this. Cool? As a consequence of the counting pattern, each position corresponds to a value that is the base raised to some power. If I have a 1, if I have a 1, 1, 1, 1, 1. That's 6 different ones. They all have a different meaning. This has the meaning, okay, 0, 1, 2, 3, 4, 5. Okay? Can you see that reasonably well over there? A 1 in this position has the meaning 1, I mean, this could be the number 2. It doesn't really matter. It's 2 times 10 to the 0. Let's do it like 1, 2, 3, 4, 5, 6. Okay? A 6 here means 6 times, because 6 is how many of ones are in there. I have 6 ones. 10 to the power of 0. This would be, I'm going to write it right to left because I'm not going to have, I'm going to mess it up. So I have 1 times 10 to the 5 plus 2 times 10 to the 4 plus 3 times 10 to the 3. What? Yeah. Plus 4 times 10 to the 2 plus 5 times 10 to the 1 plus 6 times 10 to the 0. Okay? That's what that means. If you're like, but why is it like 2 times? Well, it's like, how many ones, like I have 2 10 to the 4s, right? So just 2 times that many. Someone want to open up a calculator and type this in and tell me what you get? You don't need to, right? You're like, okay, it's obviously 123,453. Why? Well, that's 100,000 plus 20,000 plus 3,000 plus 400 plus 50 plus 6, which is obviously 123,456. Great. But that's like how we can go from the meaning of the number base 10. When I see 1, 2, 3, 4, 5, 6, oh, that means 123, because it's in base 10, and we all know that this is how it all works. But the meaning, right now I'm reminding you, don't forget about that whole meaning rant, okay? Cool. Okay, as a consequence of the counting pattern, each position corresponds to the value that it's raised to, the number 1, 2, 3. 1 times 10 to the 2, yada, yada, yada. We just did that bigger. Think of it like with money, right? It may feel strange to think about the number 123 like this, but this is what you do all the time. This is how base 10 numbers are encoded. This is how you deal with money in denominations, right? Well, here's an example with 100s, 10s, and 2. How much money do I have? Well, I have 1 100, 2 10s, and $3. Great. Cool? Cool. At this stage, none of this should be scaring you. If it is, just come talk to me. It's just thinking about base 10. But all I'm trying to do is really emphasize, what are we even doing when we're talking about base 10 numbers? That's really what I'm trying to hit here. Okay, consequence of finite digits. So, with integers, there are a finite number, there is an infinite number of leading zeros, right? They go on forever. Now, I only showed you 8, though, because I don't have room for an infinite number of zeros. I just drew 8. This means that, because I only drew 8, because I have a finite amount of space to represent these numbers on the screen, I am limited, right? There's a constraint. So the largest number I could represent with 8 digits is 9999999. 99,999,999. That's the biggest number I can represent with 8 digits. Obviously, there are numbers bigger than this, but if I'm constrained to only 8 spots, that's the biggest number I could represent. Do you agree with that statement? Cool. What would happen, just as an exercise, like a thought exercise right now? Let's say I have 9, 9, 9, 9, 9, 9, 9, 9. And I have a sheet of paper that's this big. I can't put a number, I can't fit another number on there. That's why I only have 8 spots, right? I'm limited. But I want to, we're counting, right? If we follow that pattern of counting that I said we could imply forever, infinitely, well, how does this work? Okay, we add 0, 0, 0, 0, 0, 0, 0, 0, 1. Ah, I missed the page. So, I mean, that 1 doesn't really, it's not really there. So what number comes after 99,999,999? I mean, obviously, we know it's 100 million. But if I don't have that 9th position, what came after? 0, apparently. As far as this page is concerned, it's 0. As far as anyone that looks at this paper, it's 0, which is kind of funny. But that's only a consequence of how we are limited. Like, there is a finite amount of space we have. Someone's got to draw the line somewhere because in theory there's an infinite number, but let's get real. We are limited by things in our physical spaces, right? Right. Base 2. Before I jump to base 2, does anyone have any questions about what I just ranted about? It's important that you have a reasonably good understanding of what I'm talking about. I don't expect anything to be wildly out of left field for you, but if there's anything that's just not quite right, do ask now before we carry on. Perfect. I had a good feeling about you bunch. I knew you could count. All right, binary. Base 2. Now, all of the rules that we've learned apply here. Nothing is changing except for one little detail. That we only have 2 symbols. Instead of 10, 0 through 9, we're only going to play with 2 symbols, 0 and 1. But we can do all of the same stuff. Decimal is a number that we use, or sorry, that's the system we use in everyday life. And what's wild is you go back a couple thousand years in different places of the planet, they use different number bases. You go back to the Sumerians, they're using like base 64. No, base 60, base 60. Base 60. That's wild, right? That's crazy. And it's their fault that circles are all based around 60, by the way, and 60 minutes at an hour and all that. Blame the Sumerians, right? 360 degrees in a circle. What's up with that? Yeah, it's the Sumerians' fault. So it's funny, though, that like to them, they'd look at base 10 and be like, what are you doing? That's stupid. Base 60 is way better. There are bases that are arguably better for basic arithmetic. I mean, 60 is phenomenal. It's got a lot of different like nice factors. There's a lot of reasons why 60 is really nice. 10's actually kind of terrible for like mathematics, like how we're representing numbers a lot of times. But we like it and we're stuck with it. So there we go. So decimal's the typical way we encode our numbers in everyday life. But base 10, it's only an encoding of information, right? When I have the number up 123, that has a meaning, like a magnitude meaning, right? If I write it as 123, I've encoded it as 123 in base 10. It's an encoding, but that's only an encoding. Other bases could be used. We could use base 2. Instead of 10 symbols, like I said, we only have 2, 0 and 1. 0 means 0, just like base 10, and 1 means 1, just like base 10. Remember, the symbol and its meaning are different, right? Like, how many markers am I holding in my hand? Like 1. There's a quantity there, 1. I represent that idea as a 1. But there's no like digit 1 in my hand. Like that's a stupid thing, right? Anyways, just remember, these are different things, the symbol and the meaning. So these symbols have an ordering and a magnitude, like with the decimal numbers. And the position matters, just like in base 10. The value of 1 depends on, like the meaning of the value of 1 depends on where it is. And there are an infinite number of leading zeros. 1 is equal to 0, 0, 0, 0, 0, 0, 0, 1, and 0, 0, 0, 0, 0, 1, right? Like there's an infinite number of leading zeros. All of those same rules apply. In decimal, we call them digits. In binary, We call them bits. They're called bits because they actually, it's kind of hard to tell really what it is. It seems like there's some maybe apocryphal stories. It's hard to say, but bit actually means binary information digit. I know a lot of people say like it means binary digit. No, actually it means binary information digit, or information digit, but whatever. I know, who cares? But the more you know. And the counting rules are the same. Increment to the next symbol. If there are no symbols, reset to 0 and increment the next thing. So let's count binary. 0, that means 0. What comes after 0? 1. Okay, what comes after 1? 2. 2, uh-oh, right, we don't have a 2. So what do? We reset this to the first digit, like the first symbol, 0. Go to the next one and increment. Ugh. Right? What happens? Reset. What happens? Reset. What happens? Reset. Increment the next one, 1. 0, 1, 2, 3, 4, 5, 6, 7, 8. Cool, right? I think that's cool. It follows the exact same pattern. Let's do it again on this side this time, slower. If you leave today and you don't understand this, you're going to have a bad time in this course. So make sure we understand it. And here's why it shouldn't be difficult. Look, if it's difficult, ask for clarity. Obviously, if something's not clear, I'm explaining it poorly. The rule is the same as decimal, though. It's just we only have 2 symbols. So if anything, it's easier. What comes after the symbol 0? Help me.
1.
Okay. What comes after the symbol? I have 1. What comes after the 1 symbol? 1. We don't have 1, so we got to reset to 0. But what do? Increment the next number. And what was that? Well, that was a 0. Remember, there are zeros here. So increment that 0 to be a, what comes after 0? Great. What comes after 0? What comes after 1? Yeah, 0. Oh, shit. What comes after 1? But remember, there's leading zeros, so what do we do to that 0? Increment it. That's the pattern. It's the exact same pattern as base 10, but we only have 2 symbols. Questions, thoughts, concerns, comments, observations? Yes? Yeah, yes, yes. But I mean, an odometer would be base 10, but that's exactly. An odometer, what a beautiful, I should add that to the course content. It's like an odometer, right? Think of okay, they're young. So maybe they're used to digital odometers. But think of the dial odometer. Who's driven in a car from the 90s, right? Yeah. Like this, right? These ones where they spin, right? There you go. Like an old school odometer. Right? Cool. Yeah? Happy, sad. Yeah? All right, yeah, okay. Counting rules are the same. Increment to the next symbol. If there's no more symbols, reset to 0. Increment the symbol in the next position. 0, 1, 2, 3, 4, 5, and so on. With 8 bits, the largest possible number I could represent, because remember before with 8 digits, I could represent 99,999,999. With binary, the biggest number I could actually represent is 255. I could represent all numbers between 0 and 255. Like base 10, the specific bit position carries different values. These values always are always the base to some power. And although these bit positions don't really go by specific names, they can be named like the digits. The 1s, the 2s, the 4s, the 8s, the 16s, 32s, and 64s. They all go up by a power of 2. In base 10, they all went up by a power of 10. Here they're going up by a power of 2. So if you're like, oh, that's cool, it's always doubling. Yeah, before they were always going up by 10s. We'll review here tomorrow. I'll see y'all later.